Okay.
Okay, so welcome back. Our next speaker is Misao Sasaki from Kafri IPMU, University of Tokyo, telling us about inflation as a tool to explore the physics of the early universe. Let's welcome.
Thank you. Thanks for the introduction. And I don't know who are the organizers, but I have to thank the organizers for inviting me. I didn't know that this is really huge campus. This whole campus is quite amazing. Anyway, let me start. So this is talk about some say very basic things about inflation, and it's sort of a observational implications and so on and so forth. Anyway, if you have any questions, comments, complaints, whatever, you can raise your hands, or maybe even without raising hand, just scream, please. I will try to answer your questions. Okay, so let me just first, try to be a bit sort of a provocative to talk about, this. So this is something which maybe some people think it's not the case. But anyway, so what is inflation? There are many things. By the way, there are some people's name which maybe you haven't heard much about. I mean, you know their names. They're famous particle physicists. But those people actually have a very, very nice paper on inflation. Of course, they never talk it. I said it was inflation, but it's kind of creation of the universe from nothing, born of an open universe out of Minkowski space, and they assumed that there was the exponential expanding stage. Although the energy scale at that time considered was 100 MeV or something. It's a 10 order of magnitude difference, but still they already had this idea. So that's one thing I like to emphasize a little bit. Anyway, there are so many people who are working on this inflation. And as almost everybody knows, that inflation is a quasi-exponential expansion of the universe at its very, very early stage. So now perhaps maybe at 10 to 35, 36 seconds, very early. And originally it was meant to solve the initial condition of problems in Big Bang cosmology, let's say singularity, horizon, and flat mass problems, and so on and so forth. Now we realize after almost 40 years, yes, or maybe more than 40 years, that if any of them can be said to be solved, actually depends on what you mean by solving problems or how you define the problems. And then, so this is becoming a bit philosophical. So I don't want to touch this problem anymore. This has become much less and less important, by the way, from the perspective of observational or cosmology. Most important thing is that soon after the people start to consider those exponential expanding universe, then realize quantum vacuum fluctuations are the most important things. And the most important prediction of inflation, which is quite general to many of inflation models, is that those vacuum fluctuations, whatever field, maybe it's the inflaton field which drives inflation, or some other fields, anything you want to consider, but anyway, it's the vacuum fluctuations that turns into that plays the most important role, and they give rise to the initial condition of the structures of the universe. All the structures of the universe, by the way, including us, human beings, everything. So everything in the universe which is non-trivial is due to vacuum fluctuation. This is the most important message of inflation. Yes? Okay. And of course, I mean, this is most important, and there are so many sort of observation data that supports this. But we would really want to, confirm inflation. Then this is the last bit of thing which we really want, which is related to actually the first talk today, this morning. But if there was inflation, then and if there was quantum vacuum fluctuations, and if the gravity must be quantized, then you should see some quantum gravitational sort of relics from inflation, which is the gravitational wave background. So we hope that we someday, hopefully within my lifetime, which is like 10 years, maybe 5 years, maybe 10 days, but anyway. So we'd like to see this. Anyway, so let me just go through quickly some vanilla inflation model type thing. So you have the inflaton field, which is derived, and you have some a potential which is slightly sort of has a slope towards zero, and therefore it sort of rolls down, but rolling is very slow, which is called slow rolling inflation. But after certain epoch, the kinetic energy becomes essentially equal to the potential energy. From that point, then the inflaton field would start to roll down the hill rapidly and probably, and assuming that there is a minimum, and then they start to oscillate. This oscillation leads to some small, not maybe small, but some epoch of effectively matter-dominated stage. The oscillation leads to some matter-dominated type universe. Then gradually this turns into some matter, hopefully that's standard matter fields, like electrons, quarks, neutrons, and so on and so forth, and Higgs maybe, yes. And then the universe turns into the radiation-dominant universe. So this is the typical feature that you have in the beginning during inflation. The energy density is almost essentially constant. Then after inflation, it decreases like a cube. This is the oscillatory stage. And then gradually those turned into the relativistic particles, and the universe becomes hot and dense. And this is, you could regard this as the beginning of a hot Big Bang universe. So in that sense, the inflation realized the initial condition for the hot Big Bang universe. By the way, so every time you have some scenario cosmology, everybody always asks what's the initial condition. And then initial conditions sort of important, but that important sort of question, but that question cannot be solved within that model. For example, in the Big Bang theory, you assume universe was thermal equilibrium. Yes, this is an assumption, and you cannot solve it within Big Bang cosmology. Inflation solved that problem, but inflation doesn't solve its initial condition. And the initial condition of inflation, you assume, is universe is spatially homogeneous. Okay, so this homogeneity cannot be solved within inflation. You have to have something before, and that's one thing you should always keep in mind. Okay. Any questions so far? It's okay. Around this point, maybe some people have some objections, but okay. Anyway. So a little bit more about the inflation. So as I said, homogeneity and isotropy are the most important assumption, okay? Not the concept of inflation. This is something you should keep in mind. And nowadays, more sort of confused, we are in the confused situation because after, during this, when people start talking about the inflation, there was only single model gravity, which is Einstein gravity. So there was no sort of a reason to consider some other kind of gravity or other frames now we call. Now, in the most simplest case of so-called scalar tensor gravity with some scalar field, it plays a role of additional gravitational degrees of freedom. You have a degrees of freedom of conformal transformation. So by the conformal transformation, you can go to a different frame. For example, in the standard scalar tensor theory, there's a frame called Jordan frame, where the gravitational action is not Einstein, much more complicated. While you can transform that frame to a frame where gravity looks Einstein, which is called Einstein frame. So the simplest now, the sort of definition of inflation is that we assume actually the exponential expansion is occurring in Einstein frame. And if it is not so, if you go to the Einstein frame and if the universe is not exponentially expanding, maybe you shouldn't call it. The simplest example, for example, you can always, in the simplest sort of a Friedman-Robertson Lemaitre, sorry, yeah, you have to add Lemaitre. Friedman-Lemaitre-Robertson metric. You have the scale factor times, let's say, essentially static metric. Now, if you make the conformal transformation to get rid of this scale factor, you are left with the static universe. So is this static universe? Then you say, okay, in this frame, there's no inflation. And that's true. There's no inflation on that frame because by definition, it's static. But it is because in that frame, gravity looks completely different from Einstein theory. So if you go back to Einstein frame, then you find that the universe is exponentially expanding. Anyway, so this is it. But these days, actually, the more complication is that this sort of assumes the existence of Einstein frame. Now there are so many different sort of modified gravity theories, and which doesn't allow the existence of Einstein frame. Then you have to be careful how to define it. I have some small definition, but maybe I don't have time to introduce this. Okay, another thing I said is, of course, this is related to this original horizon problem. Now, the horizon problem is not a homogeneity problem. Homogeneity, as I said, is just an assumption. But under that homogeneity assumption, there seems to be some very strong correlations on scales, which is far greater than the current Hubble scale, or maybe probably is in the past, let's say, in the Hubble scale. And to have such a correlation, actually, you now found that it's you need at least 50 or 60 number of equals of the inflation. Again, I have to emphasize we don't care what happened before inflation, but the important point, like in the case of Big Bang theory, that once you assume the thermal equilibrium, then we don't, it doesn't matter what kind of initial condition before Big Bang you had, but you have a definite prediction. Similar here, if you assume inflation, then most of the predictions become almost independent of the initial condition. And that's the power of inflation model scenario. But at the same time, this means it's the same as the Big Bang case. And, since it cannot solve initial condition problems, you have to think of some other or better or newer or more quantum theory of initial conditions. That's a next step thing. And of course, we are interested in that next step too. Okay, let me just go through the kinematics. This is a sort of a diagram you probably see in many textbooks and so on and so forth. The horizontal axis is the log of scale factor or number of e-folds. The vertical axis is the log of a scale. So if you consider a co-moving sort of a scale which expand with the expansion of the universe, then you have this straight line. Like, this is K is the co-moving wave number, which is constant, or the co-moving wavelength, whatever you like to call. While this blue line would be the Hubble horizon radius, and during inflation, it's almost constant. You have some reheating, which we still don't know what happened, but and which is another very interesting sort of things we have to explore. But anyway, after this reheating stage, we have some radiation-dominant Big Bang universe. Now we have some matter-dominant stage, and then we come back to some dark energy-dominated universe today. But I forget about that very recent time, and just focus on this in the past. Then, so this is how the Hubble horizon scale moves. And as you could see, the co-moving wavelengths, once it was inside the horizon, comes out of the horizon and goes inside the horizon again. And this is how you create seemingly super horizon scale correlations, because those super horizon, oh, by the way, the Hubble scale is the scale where the causality is, two events would be causally connected by that time of the universe. It's the local sort of a causal horizon scale. That's why sometimes we just, instead of calling the Hubble radius or Hubble horizon radius, you just simply call it horizon, although it's not a strictly horizon, but it's effectively locally a horizon. So if it is outside the horizon, it's a causal. So if you have some correlations between those large scales, causal scales, then you have to have some explanation, unless you just believe in God or something who prepared the initial conditions. And the inflation actually does this job. As you could see, this was, if you go back in time, this comes inside the Hubble radius. Therefore, this is completely, so you have some causal process can be happening here. And all this causal process can give rise to correlations today. And as I said in the previous slide, that the most important correlation comes from vacuum fluctuations on those scales. Anyway, so this is the sort of a kinematical structure or the causal structure of the inflationary universe. And as far as the flatness of the universe is concerned, this is how you explain. So let's assume that you start from very, very small universe. Again, and you assume this expansion, huge expansion of inflation. To have some successful inflation expansion of the universe, you have to assume some kind of homogeneity of the universe in the beginning. So homogeneity, I assume. Anyway, and the isotropy, by the way. And under that assumption, the universe can expand by a factor greater than 10 to 30, which to satisfy this horizon problem and so on and so forth. Then our current universe size, the horizon size, Hubble horizon scale, which I just given in this Hubble horizon scale today, today should be much, much smaller than the original size of the universe. And this means whatever the initial curvature of the space is, this looks essentially flat, very flat. I mean, like a Euclidean tree space, three-dimensional. So flatness can be explained by inflation. But of course, this doesn't mean that inflation, I mean, always imply inflation, because this depends on this assumption. Yes. If you assume the expansion was, period was lasted long enough, then you expect flat universe. But this could be short. And in that case, you may have some remaining of the initial stage of the universe. And that may have some non-trivial curvature. That's an interesting topic. Again, I mean, it cannot touch it. This is in related to initial conditions. Okay, let me just go through dynamics. So, as I said, the most important is sort of how to say, prediction is the cosmological perturbations coming from the vacuum fluctuations. And essentially, this is a simplified version, but this is essentially true. So you can trust my slides. Anyway, so if you consider some, let's say, simple slow rolling inflationary model where I have this kind of potential, then potential is very, very flat. So at leading order approximation, you can assume potential to be just a constant. If you assume that, then of course the mass of that scalar field is 0. Therefore, if you take the fluctuations, the fluctuation behaves, it follows this equation, delta phi double dot plus 3h phi dot plus omega squared delta phi. Omega squared is k squared over a squared. This is the scale factor. This is the moving wave number. H is the expansion rate of universe, which is almost constant, and because of this term, which comes from the dimension of space, 3D spatial dimension, therefore, when the universe expands, kinetic energy decays like the 8 minus q. So, so this 3 comes from that sort of essentially decay of energy density due to the expansion. But anyway, the most important point, this h is almost constant, while omega square is k square over a square. So in the beginning, when a is very small, this dominates. So in that case, you can just ignore this, and essentially this is the oscillating a harmonic oscillator. But as the scale factor expands, and this expansion is very rapid, it's exponential. So this omega square, effective sort of a what do you call, a mass term, potential, whatever, anyway, it's a frequency, decreases so rapidly that the oscillation can actually freeze out. And then it sort of goes into the so-called overdamped system. This is kind of picture I tried to draw in the movie. I hope it makes some sense to you. So gradually it goes down, and then and its potential becomes completely flat because of this friction term. And then sort of this, the delta phi sort of stops at somewhere. This stops at the position is random because initial condition, the vacuum fluctuation is random. Therefore, you create some random random vacuum fluctuation gives rise to some constant fluctuations which is random, yes, in k space. So anyway, and we know that if you start from standard vacuum fluctuations, the amplitude of this order Hubble constant. But anyway, that's what happens. Oh, by the way, exactly the same thing happens to the gravitational wave perturbations as well. Now, going back to this scale-up type perturbations, how this turns into the structure of the universe. Because the inflation ends. Again, now, if inflation continues forever, we don't have anything. You know, those fluctuations freezes out, and they apparently, under this assumption, if the potential is flat, then the value of the scale field doesn't mean anything, huh? Because it doesn't contain any energy or anything. So this means if inflation continues forever, nothing, you don't obtain anything. So the end of inflation determines everything. This is another thing you should, and in this simple model of single field slow inflation, you can sort of talk about some conservation laws and so on and so forth, and some evolution of the so-called curvature perturbation and so on and so forth. But that's essentially irrelevant as soon as you go to most, not has a general models of inflation. If you consider some most general model of inflation, 2, 3 field, whatever, then how the inflation ends determines everything. And this is how you explain. Okay, so you have some fluctuations in the beginning, but in the previous, here I completely ignore the gravity, which is a very good approximation when you are inside the horizon, Hubble horizon. Even outside the horizon, actually you find that those in this so-called flat slicing frame, where you sort of minimize the fluctuation on the space, three-dimensional space. This is called flat slicing. In this flat slicing, the effect of say gravity is always suppressed by Planck's scale. So you have the 1 over m Planck square suppression of that term, so which I completely ignored here. But anyway, which is called the flat slicing. So this curly R represents the spatial curvature of the universe. And if you can put this equal to 0, that's the choice of your gauge. And in that case, you have some non-trivial fluctuation scalar field. Now, at the end of inflation in this simple model ends by some local physics. Local physics means that if you just look at some locally in the universe, everything is determined by these fluctuations of phi or phi itself. So end of inflation must occur on the same value of scalar field at each space point. Otherwise, you violate locality. Okay, so the assumption that the local physics determines the end of inflation means that end of inflation must be in this single field model determined by the scale as slice where time slice where the scalar field fluctuation is zero. So this, in some sense, is gauge transformation, but by going to this slice, you create non-trivial curvature of the slice. And that's the beginning, how to say, when you create, say, curvature perturbation or spatial curvature perturbation or universe out of inflation. So this curvature perturbation do not exist before inflation, during inflation. Although you can write down the equation motion, but it, as I said, it doesn't really mean much. The whole thing is determined by this end of inflation surface. Okay, that's the most important point. Now, okay. To summarize, you have to say essentially the so-called slow roll inflation that you expect if the inflation lasts long enough, especially flat universe, and then since the potential is almost flat, which means that the fluctuations which you expect when they cross the horizon would be essentially the same, from here and here. It doesn't really change, and the amplitude, mean square amplitude, would be h square. Root mean square is h, which is given by this fluctuations amplitude, and so you expect the almost scale invariant, and since it's coming directly from the vacuum fluctuations, it's Gaussian in the statistical sense, and you have this tensor perturbation as well. So anyway, scale perturbation and tensor perturbation, sorry, and these all generate what we observe today. Now, these are the result of the computations that the curvature amplitude given by this h squared divided by phi dot, slow roll sort of a velocity at the time of horizon crossing during inflation. The power spectrum index, this is most important, which is given by the second derivative and the first derivative of potential. And as you could see that if the first derivative term dominates, then it's always negative. So independent of dw prime, you have very large contribution, negative contribution from the first derivative of potential. And this is just simply because as you go down the potential, the potential energy slowly decrease, which means the Hubble parameter slowly decrease, which gives rise to the sort of how to say spectrum which is small. Means that if you go back in time or if you go to infrared region, it becomes bigger and bigger. So that's essentially that's the reason. So in some sense, this is a very naive way of saying this, but this h square determines this behavior of the v prime square. And phi dot actually determines v double prime. So if phi dot moves faster, then it's negative. If phi dot becomes slower, it can give rise to positive contribution. Anyway, and as for the tensor perturbations, the amplitude is much simpler, and so you still you have a very simple formula where the spectral index actually is given in terms of ratio of this scalar tensor amplitude. And this is a famous consistent relation, and hopefully in the not too distant future that we have observations of not only the amplitude of power spectrum, but the spectrum index, which can actually, how to say, confirm or exclude the single field model of inflation. Anyway, so now let me just turn to the observational data. So as many of you know, the most sort of, how to say, fine data comes from so-called Planck satellite. And these are, this is just a full sky map of the red point is the slightly, temperature slightly higher and the blue is slightly lower. The relative fluctuation is about 10 to the minus 5. This is it's more detailed analysis. This is multiple moment or angular momentum index, and in terms, and the amplitude is sort of flat on the very long wavelength limit, small KL, which comes from this almost scaling invariant spectrum. And then you have all this oscillatory behavior, which is due to the other matter contents of the universe, let's say baryons and other things. And apparently, this red curve, which is given by some only some empirical but model, which based on inflation, which it has, they say, only a few parameters, can fit the observation data so well. And these are other sort of polarization data and so on and so forth. But anyway, a matching is how to say, surprisingly good. So this means that we are sort of almost confident that inflation is the one which explains the current structure of the universe. As for those theoretical predictions, if you assume that, well, this is sort of related to this tensor spectrum, but assume that the tensor amplitude is not too small, meaning that in this case, essentially the Hubble parameter is not too small, then we expect the current observation tells us that the energy scale of inflation is like 10 to 16 GeV. Hopefully, it is not too small than this, but anyway, so that's the expectation, hope, but still with some question mark. As for the spectral index, we have very, very fine data with like this. So within a very, very small error bar, you have the NS minus 1. Oh, by the way, the reason why instead of just simply put NS, but NS minus 1 is the historical reason. So NS equal 1 is scale invariant, which is something a bit awkward, but that's the cosmological or well, maybe astronomical tradition. So we cannot beat them. But anyway, so NS minus 1, as I said, is a slightly negative. So which can mean maybe that the second term is important. But nowadays, apparently, now we start to think that this first term, negativity of the first term is more important. But anyway, so this is the current data. As for the tensor amplitude, so again, we in the beginning sort of wanted this to be large enough. So the tensor to scale ratio, so-called, we hoped it was at least have 0.1 or so. In that case, everything fits to some vanilla model, type of model of inflation. But unfortunately, turns to be fairly small. But anyway, this is to be observed. And this is the constraints on, say, the single field solar inflation models. The horizontal axis, the primordial tilt, NS. The vertical axis is the tensor to scale ratio. And apparently, for NS, it's very, very narrowly constrained. So, but this is okay for most of the model of inflation. You have some freedom in the parameters choice of your model, and depending on your model, you could just fit to this tilt. And for example, in this sort of simplest case of a quadratic potential phi square, you could fit very well with this ns equals 0.965. But unfortunately, the amplitude of tensor to scale ratio is bigger than 0.1, which is completely excluded by the 4, 5, 6 sigma something by the current observation. Current observation tells you essentially, even by just single Planck result, it tells you that it is less than 0.05. Anyway, it's less than 0.1. And it's approaching 0.01 level today. Anyway, so this is the result. So again, let me just emphasize that the most important message of inflation is that it gives rise to all the structures in the universe. To summarize the current status, the scalar spectrum index is slightly red at about 5 sigma level. Tensor to scale ratio is less than 0.1, and which means that the energy scale of inflation is slightly less than, hopefully not too much, but at least less than 10 to 16 GeV. And then, as I said, the simple canonical models or the vanilla type model is excluded. I didn't have time to explain this model, but so the one model which fits very well is called this R square inflation. This is so in some sense a modified gravity model, but you can always, as I said, turn that into the Einstein frame. And if you go to the Einstein frame, this is just some scalar field, some particular potential plus Einstein theory. And that theory fits this the observation that best for some reason. We don't know why, but anyway, so, well, this another thing is that, as I said, in the standard sort of a single field slow inflation model, the fluctuation is directly coming from vacuum fluctuation. Therefore, there a non-Gaussian effect, non-Gaussian statistical nature is very, very small. It should be almost zero. And which is consistent, but still, you may have some, there are several hints that this may be order 1 or something. And even if it is order 1, it excludes single slow law standard model of inflation. So this gives us sort of maybe a reason to explore something which is non-canonical. And maybe this is an excuse, but anyway, so that's how we do. And so let's just go briefly on, I have 10, 20 minutes? Yeah, okay, good. So let's go think about some beyond standard or the single field slow model inflation. There are many of the proposals. One is to consider some non-canonical Kinetic term, in which case you have some non-trivial sound velocity of scalar field, and the amplitude turns to be a proportional to 1 over the sound velocity. But at the same time, it produces some non-trivial non-Gaussianity or some type, and which is proportional to 1 over CC squared. From current observations, the CS is bounded from below by 0.024 or something, but still you have some fairly large regions of space where this may be the case. Yeah, maybe the scalar field itself has a non-trivial coupling to gravity. This is sort of essentially similar to this Stravinsky model, but anyway, you may have some direct coupling to the curvature from the beginning. In this case, you expect the curvature at a scalar tensor ratio, if Xi is large, to be a proportional to 1 over Xi. So this is a bit unfortunate. If this Xi is too large, then R becomes very small, and so you will have no chance of seeing it. In some sense, this kind of changes the effective Planck scale, and that's the reason why you have this suppression. But anyway, so that's something you may have. Also, recently, there are models of inflation which solely uses the Higgs field we know. So Higgs as an inflaton. But in this case, you do need this non-trivial coupling, and the coupling is very large. But anyway, so that's the one model. You may have some non-trivial derivative couplings, and those models are called Holdensky model, not inflation, the model of modified gravity. In this case, generally in the original frame, you have not only the sound velocity of the scalar mode less than unity, but also the tensor mode can become less than unity. The whole point is, but then this is where the complication begins. So in many of this Holdensky gravity, there exists no Einstein frame. But at least perturbatively, if you just expand the action to the second order, you can always bring the action into the frame where the sound velocity of tensor is 1, and which you can call quasi-Einstein frame. Then probably we have to define, this is my definition, define the inflation in that frame, where the tensor mode propagate at the speed of light. But that's nobody, I mean, this is my just suggestion that it has not been tested anyway. You have other multi-field models and non-attractor inflation and so on, so forth. These I may have time to explain it later. But anyway, so, and there are some hints already in the CMB scale. You have some hints on from very large scale, L smaller, less than 10. Expected, especially the L equal 2, this is the observation data. The observation data is far below the expected amplitude. Of course, since in the case of L equal 2, you have only 5 degrees of freedom. So, the so-called cosmic variance is so large. We may be just in the universe where the L equal 2 modes happen to be small. So this cosmic variance cannot be really removed unless you do some other different type of thinking. But anyway, at the moment, this is what we have. We have some, when you do more closely from the deviation from the simple model of the red curve, then you start to see some anomalies, which you may regard this as significant or non-significant. It depends on what you want to do. But anyway, so this led to many people to the ideas that maybe there are some interesting sort of physics going on during inflation. Anyway, one thing again, yes, let me just emphasize this part. This suppression of this very large scale mode may be due to some this is demonstration of some relics from the initial condition of the universe. So this led us to some idea of open inflation and so on and so forth. But of course, it's very difficult to realize now. Anyway, now that we have all this, the Niles just mentioned in his talk as well, but you have maybe 10 to 500, even more sort of vacuum, and so you may have some, we may have some interesting transition between those false vacuum and even the one, as I said, oops. Wait a minute. Where did I go? Yeah, oops. Oh, yeah. Is this, yeah. Okay, so maybe not only this, but other sort of things could be related to some kind of transition, phase transition or vacuum transition during inflation and so on and so forth. So that's an interesting sort of things or the sort of directions to pursue. Here, let me focus on some, for the last maybe 10 minutes, on some new physics on small scales. Again, these are on large scales. These are on very large scales. Large scale means that L, say, less than 1,000. But if you go to a very small scale, or very high L, the CMB won't be able to measure or detect anything from the primordial universe because of the highly sort of nonlinear astrophysical processes and so on and so forth. While gravitational wave will not be affected by those sort of evolution of the universe. They simply, their interaction with the matter is so weak that they propagate until today if they are born in the early universe today without being interfered. Anyway, so maybe if you go to a very small scale, let's say the scale, the current, say, moving scale of 1 parsec, which is like 9 order of magnitude, 10 order of magnitude, smaller than the scale we are observing today in cosmologically, then you have no chance of seeing anything from this inflation in electromagnetic waves, but you could see them by gravitational waves. And then maybe there are some interesting things going on here, and which can result in something which is observable. And one of the things which is currently pursued a lot is the primordial black holes. The primordial black holes, those are formed in the very early universe, when essentially universe was radiation dominated. So because of radiation pressure, you cannot really form a gravitational collapse. But horizon-sized universe, the universe which is at the Hubble horizon scale, can collapse. And this is essentially, as you go back to your undergrad stage where you done maybe the Friedmann equation in the beginning, then you are taught that there are 3 different models of a universe: open, a flat, and closed universe. Closed universe has the positive curvature, spatial curvature, and this positive spatial curvature universe once expands, but have some maximum radius, and at the maximum radius, the Hubble expansion stops and start to collapse again. And this is due to the positive spatial curvature. Now, essentially the same thing happens in the universe. If you consider a local universe, and as the universe expands, and if the local universe, region of some local universe becomes the size of the Hubble horizon scale, and within which you have the positive, this is important, positive curvature perturbations, large scale positive curvature perturbation on that scale, then this universe locally behaves like closed universe, and they start to collapse. So that's how you form a primordial black hole. Primordial black hole is not from the standard gravitational collapse because radiation pressure is too strong to avoid collapsing of anything. However, the horizon scale region can collapse due to the positive curvature. So then the mass of black hole would be the horizon scale at the moment when the scale becomes equal to the horizon scale. So then the mass would be given by this time at which this scale crossed the horizon. It's about 100 MeV. It's 1 solar mass, or correspond to 1 parsec in co-moving scale. So this is an interesting scale. of where we might have something happen in that early universe. Anyway, now, there are, of course, observational constraints on the amount of primordial black holes, mostly coming from sort of gravitational lensing events. But, by the way, the left side, this constraint comes from the Hawking evaporation. If the Hawking evaporation happens in the standard manner, then essentially, if the mass is small, like 10 to 15 grams or something, they are just evaporating today and emitting lots of gamma rays and so on. But since we don't see those gamma rays, that gives you a very strong constraint on the number of primordial black holes. There is some small interesting window of about 10 to 20 grams of black hole mass, because if the mass is this size, 10 to 20, then the size of black hole is less than the wavelengths of optical light, which means that you cannot have any observation of those, how to say, this diffraction effect. So you don't see them, which means that unless you have some very, very nice, interesting point like a gamma ray source in the far away, this is very difficult to exclude. So at least from current observational data, this is completely free, region. So so this means that actually primordial black holes of mass of about 10 to 20 grams can be a dark matter of the universe. Other interesting region is this LIGO-VAGO, the Kagura, LVK, this is they call black holes. According to what they have found in all these interferometer experiments, there seems to be lots of fairly massive black hole binaries. And maybe not all of them, but maybe some of them, or maybe, yes, almost all of them, may be primordial. In that case, there is sort of a, amount would be about 1% or 0.1% or something. But in any case, so if this is the case, then in the future interferometer, when you start to see a high redshift events more and more, then if it is astrophysical, then of course, those event rate at very high redshift to decrease. While if they are primordial, the event rate essentially is a constant. It's redshift. Therefore, you can test this model. Anyway, so that's an interesting sort of reasons. Now, more interesting is that this, from our sort of a point of view, that if this curvature perturbation is the source of all the structure of the universe, including primordial black holes. Now, if there is a region which the curvature perturbation is so huge over the 1, then that region turns into black hole. But most of the region of the universe, the fluctuations are not so huge. So those not so large fluctuation regions, when they enter the horizon, just start oscillate. And it's during the radiation-dominant universe, they behave like sound waves. Now, those sound waves at second order, of course, they have the energy density. And you have the energy density fluctuation. If you have the energy density fluctuations, you produce gravitational wave. So you produce some gravitational wave background due to the fairly large curvature perturbations, but not too large. And these two are completely correlated. Mass of black hole and frequency of gravitational waves are correlated. And for example, if primordial black holes are dark matter of the universe with mass of 10 to 21 grams, then frequency of those gravitational waves would be 10 to minus 3 hertz. That's exactly in the LISA band. LISA is the future interferometer in space, hopefully to be launched within 10 years. Yes. Anyway, if the primordial black holes at LIGO-VAGO and Kagura black holes with the mass of, say, 10 solar mass or something, then the associated gravitational wave frequency will be 10 to minus 8 hertz. Actually, this is related to this recently defined nanohertz gravitational waves, but one order of magnitude smaller, which means that the mass is also small. But anyway, this also can be tested by at least in the future pulsar timing array. Anyway, so I guess probably I should just go through. This is just the case whether this this non-Gaussianity I just touched on can affect those predictions and so on and so forth. And apparently in the simple model of those non-Gaussianity, we found that the amplitude of those produced gravitational wave would be large enough if the whole dark matter actually is composed of primordial black holes. Anyway, and then we, as I just mentioned, we just recently had some very interesting news last year that at the pulsar timing array sort of collaborations, or they found some non-trivial evidence of the non-trivial gravitational wave background. And if they the induced gravitational wave background are gravitational waves from those large curvature perturbations, then amplitude of those curvature perturbations should be about 0.1, which may be a little bit too large, but still not inconsistent with at least linear theory. So this is another very interesting sort of things which we hope to be tested after maybe 10 more years or so. We accumulate more data of pulsar timing array, then we will see if those are really the induced gravitational wave or not. Now let me just quickly go through the future issue. As I keep saying that we have this question about how to define inflation. I mean, it's more philosophical maybe, but anyway, in a proper way so that everybody has the unique sort of predictions. Once you are given the model, let's say of inflation, if depending on the different frames, if the prediction differs, then something's apparently wrong. So we have to have some definite predictions. And the one most important thing, of course, in here is that although we may have some small variation of general relativity, maybe those Lorentz variation, whatever, but at leading order, Einstein theory is a very good theory to describe the current universe. So that actually means that if there exists Einstein frame, you should work in Einstein frame. That's the best. But if you don't, you have to find the frame which is closest to the Einstein frame. Anyway, we don't know about initial condition, as I said. Maybe it's multiverse things, maybe this string landscape thing, and there are some hints of those things, so we definitely go into this. One thing I didn't touch, but it's almost very, very important, is that we need to have some successful reheating, and at the same time, as one of the another most important sort of a question in the cosmology is baryon number. And we have to explain baryon number, and which may be explained by this reheating from inflation, maybe later time, but anyway, this is more important in some sense. Non-linearity, non-Gaussianities, and those gravitational wave and so on. Suppose I actually mentioned, but anyway, of course, in the end, we do have to identify inflaton, if it is. And we are sort of starting to be in the era of observational or experimental inflationary cosmology. So, thank you.
So we have time for questions.
So very nice, thanks a lot. So I was just wondering, the gravitational waves you think can be produced by when you make primordial black holes. So usually you think these are very spherical because they're I mean, they're rare, and rare peaks at Gaussian random fields
Right.
are very spherical.
Yeah.
So then you don't expect a lot of gravitational waves if they're spherical, but I guess you want some small deviations from sphericity.
Oh, no. Yeah. I mean, so this is it's something, maybe I should have explained it more carefully. So this and this is a different thing. Let's say you have this is space, and you have fluctuations. Somewhere you have peak, yes? And this goes into probably a black hole. The remaining gravitational waves.
Oh, I see.
Yeah.
So the rest of them are.
Yeah,
Okay,
that's
thanks.
right. Mhm.
I've heard it claimed that the very large scale anomalies look like some kind of parity violation.
Oh, yeah. Well, yes. Actually, I mean, not given here. Yes, but there's some hints. Yes, of parity violation. Yes, right. And if that's the case, that of course. I mean, I don't have any models of such case, but that would be very interesting. Yes.
So you agree there are some hints that look.
There are some hints, but it's always, like 1 sigma, 2 sigma level. So you cannot really say it's really the evidence, but you can sort of pursue that possibilities also. Yeah.
Hello, can you explain again why Sobrinsky is the best fit?
Why Stravinsky is best fit? Ooh, I don't really know why. Apparently, when you, well, this is, I don't have a very good way to explain this, but when you have the pure R square, and if you try transform that into the Einstein frame, then you have some sort of a flat region plus some exponentially sort of a decaying potential. And this exponential behavior is quite common to all these conformal transformation things. I have no idea how to explain this, but anyway, and this just fits this because the whole point, oh yes, this negative, slightly negative, huh? Slightly negative actually means either this is negative or this wins. But if this wins, actually this ratio becomes large. But now we know that the ratio is less than 0.1 or 0.01 and so on. This means that the second term cannot dominate. Then you need this negative second derivative. And this can be very easily sort of given by this kind of potential which goes like this. Huh? Yeah. So with some flat region and going down. And this was exactly what is sort of given by the Stravinsky model of inflation.
So another thing I noticed that Sobrinsky is that you modify the action. So maybe it's more fundamental than the other, like single field or multiple fields.
Sorry, what's the?
I mean, Stravinsky is that you modify the action, so maybe it's more fundamental than the other, the single field.
Well, I'm not sure whether it's more fundamental or not, but at least in this case, if you can explain why. By the way, if this question the R square must be very large. In non-dimensional units, like 10,000 or maybe 100,000. So, but the higher order terms must be suppressed by at least smaller than order 1. If the higher order R cube and R force, and if those start to play a role, then this breaks down. So this, I don't know. I mean, it does fit the current observation data, but we don't really know why the correction ends. In this case, correction ends only at R square. If there's a very interesting reason, then that's something, yes. could be very interesting. Yes. No, he had a question. Yes, first.
So I would like to get back to this picture that you
Yes.
drew there. So you said that they are like solar mass black holes, because I was always under the
Oh,
impression that the standard
I mean, this is a scaling equation.
because the PTA is usually explained by supermassive black hole background, right? But here you are.
Oh, no. That's okay. So again, so the one explanation is the supermassive black hole binaries. So in this case, the prediction is this dotted line, and this dotted line is, I think so. Yes, doesn't really fit with the data. Yeah, as you see, if the data predicts this line, the green blue, so the dot line doesn't really fit. Therefore, as far as their analysis is concerned, the best fit data, the best fit model is the induced gravitational wave. This fits best.
So I kind of missed, how is that gravitational wave induced?
So it's nothing to this supermassive black hole, but in this case, this black hole is about, say, 0.1 solar mass.
So the black hole is just the tail of the distribution.
Oh, yeah, that's right.
So to say, and the rest of the distribution gives you so the same distribution gives you as in the bulk the gravitational wave.
So those main part, this comes from essentially say root sigma, or the power spectrum, yes, sigma square. So if you have the probability distribution function, let's say this is some amplitude, let's say delta, and this is probability distribution function, then this would be the sigma, right? And this gives rise to the background, this amplitude, while this tail part gives rise to PBH. So everything depends very much on how the tail behaves, yes.
I see, well, Gaussian statistics.
Yeah. So in the case of Gaussian, we know, and that's the only case we know. But if it deviates from Gaussian statistics, there are many sort of models proposed these days. But at the moment, we don't really know how to compute the amount of PBH.
Okay, thank you.
Yeah.
So going back to the previous question about the RS squared that Mr. Rollin was asking. So there is something special about RS squared, which I think Bob Oldham has worked on as well, as this quadratic gravity is a renormalizable theory of gravity. So they don't have to be higher order terms in principle. Now there is a small issue of ghosts being part of the quadratic gravity, but if you ignore that issue, then
Well, probably depends on how you look at it. I mean, so you say if you go to higher order, we don't know how to control. Therefore, assume that everything is stopped here.
It is a renormalizable theory.
In some very naive sense, yes. Well, we can discuss later.
Right. No, but like Estella proved that quadratic gravity is renormalizable. So with the wireless square term, but
Forget about ghost as well. But as far as I understand, this is done in a pure gravity level. And as soon as you couple the matter field, then, for example, if you go to the Einstein parameter, in this simple model, a potential is non-normalizable, right? So it sort of depends on which direction you approach things. But anyway, I still think that this phi is an important question.
Okay, more questions? Yeah, I actually have a small question on your last slide when you mentioned 0.1 may be too large for the fluctuation.
Oh, yeah.
Would you worry about loop corrections in this case, since there are so many debates recently on the importance of loop correction? So what's your take?
Well, interesting point. But I think at least, although there are some still controversies, but people, or both sides people, they start to agree that at least if the transition was smooth enough, then you don't have this issue. So in that sense, one loop may be important or have some implications, but at least you have some models where this problem doesn't occur. Yeah, model dependent, let's say, yes.
So more questions? So if no, let's thank Sasaki-san again.
Thank you.